Start the webinar, and now we can wait a few minutes. Yeah, to give people an opportunity to attend, and then I will introduce you, and yeah, and we see from there. Let's wait just a minute that everybody joins. Okay, let's wait another 30 seconds and then we start. Okay, I think we waited a few minutes, we can start. So good morning, everyone. Welcome to this edition of Data at Breakfast. My name is Francesco Petroccione, and I'm responsible for making you wake up early on Friday mornings. Yeah? This morning, I'm very happy to introduce to you Dr. Makhamisa Senekane. Makhamisa did his undergraduate studies at the National University of Lesotho. Then he did his master's in electrical engineering, if I remember correctly, at UCT, and his PhD in quantum technology at UKZN. Yeah. After that, he became a lecturer at the National University of Lesotho, and since a couple of months, he's a senior researcher at the Institute for Intelligent Systems of the University of Johannesburg. Yeah? But the reason we invited him this morning is that he very recently published a book, yeah, that is called Hands-on Quantum Information Processing with Python. Yeah? And we are very happy that he accepted to join us this morning and share with us some background on the on the coming together of his book, yeah, because it's a book that will be useful to many students that are entering the field of quantum computing for the first time. So Makhamisa, thank you very much for being with us. You already started sharing your screen, and you're welcome to start your presentation now. And this morning with us on the panel are also Professor Sinaisky and Dr. Yazira Ismail. And I asked Yazira, who is also working on quantum computing and quantum communication at UKZN, to moderate the questions after the session. So please make use of the Q&A facility or raise your hand to ask questions after or during the talk. So Makhamisa, thank you very much. We are looking forward to listen to the background history of your book.
Okay, thank you very much, Prof. I think the book is mainly an introduction to quantum information processing, but it focuses more on the hands-on part of it because it's using Python, as I'll explain in a moment. So I think we started working on the books last year around March, around this time last year. Then it was published earlier this year through the Pact Publishing. It's mainly a tech book, not necessarily a textbook, but it's more for technology, to introduce people to technology people to quantum computing and quantum information processing in general. So my talk today, I was hoping to present some of the examples from the book, but I'm not sure if we'll have enough time for that. But this is the outline of what I'll cover today. I'll just provide a brief introduction, like how the book, the idea of the book, why it was published, why we worked on it, and then some few examples, and then start working on the introduction to quantum information processing, focusing mainly on quantum circuits, quantum communication, quantum algorithms, and games and cryptography. But from the book, we also cover quantum machine learning. But I know through the Data at Breakfast, there are at least 2 people who normally talk about quantum machine learning. So I think people might be familiar with that, together with continuous variable QIP. So this will be the focus of the talk today. This is the book that Prof was talking about. It's Introduction to Quantum Information Processing with Python. I think I'll justify why I went for Python in this book. So it was published earlier this, I think it was in January when it was published by its publishers, as you can see. So the idea of the book is to provide a step-by-step introduction to quantum information processing in a way that most people could understand what is happening. And we settled for the language of Python because Python, most of the tools within quantum information processing use Python. And not only that, it's almost a de facto programming language for QIP. So that's why we went for Python. It's the other thing also, which is very important, is that it's an open source language. So there's no need for people to register or have a closed source licensing. So it's a very good tool. That's why we opted for Python. The other issue is that most of the examples from the book can be run on the cloud-based Google Colab. Colab is good, especially for people who are working who are developers in a resource constrained environment. It might not be easy for people to have state-of-the-art or top-of-the-range computing devices. So with Colab, people can just use the cloud to run the code that they have, especially with Python. So that's why some of the examples from the book use Google Colab for implementations. So the target audience mainly is the software developers because there is a need to attract more, because quantum information processing itself is very broad. It's a broad church, if I could say. So it's important to attract more software developers into the community in order to have, mainly to make sure that QIP programming part of it is very frictionless. People shouldn't feel the pain of having to know everything about QIP before they could run a program on any of QIP subfields. So the audience is mainly software developers for them to be familiar with quantum information processing. Then from there, they can assist with more tools that could make life easier for physicists and mathematicians. It's also good for early stage physicists who might want to be exposed to quantum information processing. The same is also the case with some of the mathematicians who might want to learn more about QIP. So this is what we're targeting when we are writing this book. This is the target audience for us. I hope this is not slow enough. So I've just talked about the book. Now I think it's important to introduce what we mean by quantum information processing, even though it might be familiar to most of us. I think the key idea is that it explains some of the quantum mechanical principles in order to enable information processing. We're familiar with the normal information processing, like the phone that I'm using now or any other computer. It normally uses conventional information processing because it uses what we call classical physics. But with QIP or quantum information processing, it uses quantum mechanical concepts in order to allow the processing of data. Its key advantage is that so can you hear me, Prof? Hello?
Yes, Makhamisa, we can hear you. We can hear you. Sorry, I was muted.
I thought my phone, okay.
And my screen, we can't see you anymore, but we can hear you.
Let me see what happened. Let me go back to the meeting. I don't know. Oh, I should be back now.
Can you see my screen? Yes, now we can see you clearly. Thank you very much.
Thanks, bro. As I was saying, with QIP, we use quantum mechanical concepts. So the idea is to have processing which is much better than the normal information processing that we are familiar with. So there should be an added advantage to that. So quantum information processing has various fields, but in this book, some of the fields that we focused on were in quantum communication, quantum cryptography, quantum computing, and quantum error correction. But this list is not exhaustive. There are other subfields that were not included in the book, but that might be necessary in future. But for introductory part, these are the most familiar ones. So we have, with the conventional information processing, we normally use what we call a bit. So you should be familiar with bit or a binary digit, which is a basic unit of information, conventional information processing. But with QIP, we use what we call a qubit or a quantum bit. So a quantum bit is expressed as given in this equation one. It's just a superposition of two basis states. In this case, it's state 0 and state 1, with this complex coefficients alpha and beta, and they should have, this condition should for equation 2 should hold that the squares of the amplitude of the squares of those coefficients should add up to 1. So this alpha and beta are called probability amplitudes. So this is how a bit can be expressed mathematically, but there are other ways of expressing a bit, including using the block sphere, which is a geometric representation. So in this case, I was just focusing on the mathematical one, but in the book, we also go through the geometric representation of a qubit. So qubit, with quantum information processing, we can use like qubits like that I've just mentioned, which is what you call discrete variable quantum information processing. We can also use what you call continuous variable quantum information processing. So I tried to cover both these two in the book, but for now, just focus on the first, on the discrete variable, because the continuous variable, I think it's covered by at least 2 speakers that I know of. So I'll just focus on the discrete variable ones. So in order to perform this information processing, we might need to build some circuits. So in the classical world or in the conventional world, we're familiar with building different circuits to obtain a certain objective. So it's also the case with the quantum computers and quantum information processing systems. So these circuits are composed of what you call quantum gates. Like we know in the conventional computing, we have what you call gates, like the OR gate and the AND gate. There are many XOR gates, there are many gates. So even with the quantum information processing, we also have quantum gates that form quantum circuits. So they also operate on the qubits, and by operating on the qubits, they transform the qubit maybe from one state to another. So this state of operations can either be what you call unitary, meaning they can be reversible, can move from, by applying that gate to the qubit, you can reverse the operation that you did earlier, or they can be non-reversible. Non-reversible ones, irreversible ones are actually the measurements, which the measurement normally happens at the end of the computation or any processing that is being done. So the quantum gates that we're talking about can either be single qubit, meaning they act on a single qubit, or they can act on multiple qubits. In that case, there'll be multi qubit gates. So examples of single qubit gates include what you call the X gate, which just negates the Y gate and the Z gate, and other phase shift gates for single qubits. The examples of multi-qubit gates are what you call the CNOT gate, which is normally used for entanglement. We'll see some of the benefits of entanglement in a moment. We can also have some three-qubit gates like Fredkin and Toffoli gates. These are the examples of the multi-qubit gates. So having introduced a bit of quantum circuits, we can see how those circuits can be used in 2 protocols that I'll be talking about in a moment for quantum communication. These protocols are what you call quantum teleportation and quantum superdense coding. So with quantum teleportation, the idea is to transmit the quantum state, which is any arbitrary quantum state, from one location to another. If there are 2 parties, maybe Alice and Bob, Alice wants to communicate the quantum state from her side to Bob's side, she can use this, they can use this what you call quantum teleportation. So the key resource in that, like I mentioned earlier about the CNOT gate, which is used for as an entangling gate. The key resource for quantum teleportation is entanglement. So entanglement is a very key resource in that aspect. Hello?
Yeah, Makhamisa, we can hear you. We can hear you. We just can't see you anymore, but we can hear you.
Yeah, and your cell is again in vertical position.
Yeah, the slides are a bit small. Are you still there, Makhamisa? Okay, we seem to have lost our speaker. Let's give him a chance to reconnect. Maybe his internet connection is a little bit unstable at the moment. Let's wait a minute or two and see if he comes back. I will try to send him a WhatsApp in the meantime to see if we can get hold of him. Okay, let's see. Let's wait a minute or two and see what happens. I just sent him a message, but has not yet replied. Zira, do you have any slides to entertain our audience?
I thought as much you're going to ask me that. Let's give Makhamisa a few more minutes to come back.
Okay, I'm sure he'll be back in a second.
Otherwise, we have a brief discussion on how quantum technology is growing in the field and in South Africa.
Yeah, maybe we can. Yeah, or maybe maybe our participants have some questions that we can try to answer. Please raise your hand. Yeah. Okay. Here he comes. Here he comes. Okay, thank you for bearing with us. Makhamisa, can you hear us again?
Prof.
Yeah, we can.
My apologies, it's like the signal went off, so now can I use the laptop now?
You can lose.
Apologies for that. I'm really sorry.
No worries. These things happen. You're welcome to share the screen again and continue. We are just waiting for you.
Okay, Prof.
Okay, we just need to be patient another few seconds until probably the presentation comes up again on the laptop. Okay, looks like we are in business.
Okay. Thank you.
Fantastic. Thank you, Makhamisa. Welcome back.
Thank you, and apologies for that. My sincere apologies. Apologies. I think I was on quantum teleportation before.
Perfect. Yeah.
So I was saying the idea of quantum teleportation is to ensure that Alice can transmit any arbitrary quantum state to Bob. Normally they use classical channel for communication, but they just need one. They just need that two bits to transmit a single quantum state. So this is the circuit, like I said about quantum circuits. This is the circuit. The idea is for Alice to transmit this state psi here to Bob. But initially they start with an entangled state here, which is this state here. they have an entangled state, and then using that state, Alice can apply. This is the CNOT gate followed by the Haramat gate, which is a single qubit gate. This one we know that is a multi-qubit or 2-qubit gate. And then after applying these gate operations, she performs measurement here. So depending on the state, on the values that she gets from this, she can communicate with Bob on which gate Bob should apply on his side. So this is the X gate and the Z gate. These are the gates that Bob can apply on his side. So these gates, if Alice measures 0 from this state that she wants to submit, and then 1 from this EPR pair that she's sharing, if it's 0, 0, then she'll communicate to Bob that Bob should not do anything because the state will be in the state that it was sent with. But if she measures 0, 1, then she'll communicate to Bob that Bob should apply the X gate, which is this gate here, to the state so that the psi remains the same that is the one that was prepared from Alice this side. In the case of 1, 0, then Bob will apply the Z gate. If it's 1, 1, he applies both the X and the Z gates here. So this is basically how the quantum teleportation works. Another communication protocol is what you call superdense coding. It's more, in a way, it's a bit related to quantum teleportation, but in this case, it's not about transmitting the quantum state using two bits. It's about using a single quantum state in order to transmit two classical bits. So it's more like coding data into a single quantum state. So it's intended to send 2 classical bits from one communicating party to another using a single quantum state. It also uses both Bob and Alice should also be entangled before the start of the protocol of this communication protocol. So if the bits that need to be sent are 0 and 0, the operation that will be applied on the side will be just nothing will be done. But if they have to apply 0, 1 from that state, then the operation will be Z. The same if they want to communicate 1, 1. This is how these are the operations that they will apply. I hope if we have enough time, I'll go through this maybe in the code, but it might take longer also to connect to the Google Colab server. So another topic that we covered in the book is the topic on quantum algorithms. There are several quantum algorithms, but for this talk, I only chose one, but in the book we covered about several of them, not just one, but there are many, I think about around 7. So once we have quantum circuits, like we talked about quantum circuits earlier, we can use those quantum circuits to develop quantum algorithms. So an algorithm, like we know in conventional computing, if we want to perform a certain task, we can run an algorithm which is like more of a recipe of steps to be followed. So a quantum algorithm is also a sequence of instructions that are used to solve the problem. So it uses quantum, in this case, unlike the conventional computing, the quantum algorithm use some of the concepts of quantum mechanics in order to have an advantage over classical counterparts. So one of the benefits of going to QIP in general is to have that advantage over the conventional information processing devices that we are currently having. So as an algorithm, algorithms are normally implemented using circuits that are meant to implement them. So by constructing certain circuits, we can implement some of the quantum algorithms that are of interest. So typically, a quantum algorithm follows the following steps. The first step is about the initialization. The state should be prepared. After initialization, then is to introduce the Haramat gate, which is responsible for introducing superposition of the quantum states. Then a series of unitary evolutions should be implemented, and then finally at the end of the algorithm, a measurement should be performed. So these are typically 4 steps that are done: preparation, superposition, introduction of superposition, unitary evolutions, and then finally measurements. So one of the examples of the quantum algorithms is what you call a Deutsch algorithm, which is like historically is the first algorithm which was used to show that quantum computing can have benefits over conventional computing. So the idea was introduced by or proposed by David Deutsch to show that a quantum computer can perform a faster task than a conventional computer. So the idea of this algorithm is to determine whether a function, what you call a binary function, which takes 0 and each outputs 0 and 1 and takes 0 and 1 as inputs, is to determine whether such a function can be constant or balanced. Constant would mean that if you get f of x, would it give the same outcome throughout, or would it change? If it gives equal number of zeros and ones, then it's balanced. If it gives the same output throughout, regardless of the inputs, then it's a constant function. So the idea of the Deutsch algorithm is to check if you can query query your oracle to determine whether the binary function is constant or balanced. With a conventional computer, we normally will have to do that twice, first with input 0 and then with input 1. But with Deutsch algorithm, that can be done only once. So this task is performed with a single query as opposed to 2 queries. So that's one of the benefits of the Deutsch algorithm. It has that advantage over the conventional computing, which is what is necessary. So this is the second of the implementation of the Deutsch algorithm. Initialization, normally quantum states are initialized at 0. So for Deutsch algorithm, the inputs should be 0 and 1. That's why for this is x, the first one is x, this one is y. So this for y, because it has to be 1, it has to go through the x gate, which negates the state. If it's 0 for x gate, if the input is 0, the output will be 1. If the input is 1, the output will be 0. It just negates the state. So from this, we'll have the state being prepared, and then these states go through the Haramat gates, which are used for superposition, and then we have this F unitary, which is used for evaluation, and then which is that unitary function that I talked about, and then eventually we perform measurement. So basically, this is how the Deutsch algorithm is implemented. And then, other than quantum algorithms, we also touched on quantum games, because game theory is very much important in the conventional computing. So we also wanted to cover a bit on some of the quantum games. So a quantum game is any system that can be manipulated by 2 or more parties or agents, and where the payoff of the moves from these parties can be reasonably quantified. So like we know with conventional game theory, the idea is to have 2 players that are interacting, 2 or more players, depending on the nature of the game, and with the objective, if the objective of maximizing the payoff, which is what is being maximized. So even with the quantum game theory, this is the whole idea, but now we're talking about quantum systems. So these are some of the elements that constitute a quantum game: the number of players, strategies, the pair of functionals, the initial state, and the Hilbert space. So there are various quantum games that have been proposed, one of which is the CHSH game. I think we are familiar with the CHSH test for non-locality. So this game involves 2 players, Alice and Bob in this case. They receive two bits, which are X and Y, from the referee. Before the start of the game, they can communicate, but once the game starts, they are not allowed to communicate. But the referee can individually approach them, maybe to give them these bits X or Y. And then with this input, they respond with A and B. Alice will respond with A, and then Bob will respond with B. So the objective is for them to win if this condition is met here. A, X, or B is the same as X, A, X, and Y. So this game cannot be done with, because it uses CHSH, it cannot be done with classical or conventional game theory. So it relies on entanglement for it. It's non-local, so it relies on an entanglement for it to operate. So this is the procedure for implementing this game. Before the start of the game, both Alice and Alice share a bell pair. That's why they have this EPR pair that they share which is meaning they use entanglement as a resource. And then if Alice receives as input from the referee the value of X, which is 0, she measures a qubit and outputs the results. However, if she receives 1 from the referee, she applies the rotation, which is gate. She applies this gate Ry pi over 2, and then measures a qubit. On the other side, for Bob, if he receives 0, he applies the rotation Ry along y-axis pi over 4. However, if she receives state 1, he applies this rotation gate here, and then measures a qubit. The last part which I wanted to talk about today is quantum cryptography. We all, in the book, what we also did was to try to start with conventional cryptography, like with all these other topics we are studying with what we already know, like quantum cryptography or quantum conventional game theory, and then build up from there into the quantum realm. That's the approach that we're using. So we're familiar with cryptography, which is used to protect data or to secure data. So quantum cryptography also uses quantum mechanics also to secure data in this case. It's a cryptographic approach that uses quantum mechanical concepts. Normally, it can use entanglement for other QKD protocols, so it can use superposition or the node cloning theorem, which states that the quantum state, an arbitrary quantum state cannot be cloned with absolute accuracy. So there are different, like with conventional cryptography, we have different primitives like a pseudo-random generator and some of the key distribution protocols like Diffie-Hellman and all of them. It's also the case with the quantum cryptography. There are different primitives like QRND, which is the quantum random number generator, and the quantum key distribution, QKD. So QKD, historically, it was proposed, the first proposal of it was in 1984. The first QKD protocol was in 1984. So the way it operates, it uses 2 channels. One channel is called the quantum channel, where the quantum communication takes between the communicator Alice and the transmitter Alice and the receiver Bob takes place. It's in this quantum channel. But also Alice and Bob also need to communicate through the classical channel, which is this channel here, mainly for post-processing. So this is how it happens. The idea of this protocol is to ensure that an eavesdropper can be detected. If someone tries to eavesdrop into the communication, it could be easier for them to be detected by this protocol. So it goes through different steps. Like I said, within this channel, it will be, within quantum channel, it will be quantum communication, and then here it will be classical post-processing. So this quantum transmission happens at the quantum channel, and then the rest here are classical post-processing. The next step will be to sift whatever signals are received, and then to apply error correction to ensure that the errors that occurred could be corrected, and then eventually to apply privacy amplification, which is normally hashing, to ensure that any information that it might have leaked to an eavesdropper could be compressed to be as slow as possible, to be in order to ensure that the protocol is secure. There are different QKD protocols. Like I said, the first one was proposed in 1984, which is now known as the BB84 protocol. It was proposed by Bennett and Brassard. That's why it's called BB84. And then we also have the B92 protocol, which was just proposed in 1992. And then SAG04 proposed in 2004. These 3 protocols are what we call prepare and measure protocols. Alice prepares the state and then sends it over to Bob, who then performs measurement. But there's also another protocol called the E91 protocol. This list of protocols is not exhaustive. So this E91 protocol uses entanglement. So the communication will be based on entangled states between Alice and Bob. So it's not about one party preparing the other measuring. It's about having the entangled source and then having two these parties both performing measurements. I think that's the end. I'm not sure if there are some questions. In the meantime, I might try to connect to the Google Colab for some demonstrations.
Yeah, Makhamisa, thank you very much for the nice description of the content of your book. I see there are already some questions. I don't know if Yazira, would you like to guide us through the question session?
Okay, so thank you, Francesco, and thank you, Makhamisa, for sharing insights to your book on a hands-on introduction to quantum information processing. There is a question in the chat, however, it's not related to the webinar itself of the talk, so it's a linguistic question. So maybe, Makhamisa, we look forward to looking at the code that you want to present to us.
Okay,
I'm sure everyone's interested in seeing the code as well.
The hands-on part. Okay, let me just do so.
As well as please use the feature of the Q&A to post questions to Dr. Senekane.
And Makhamisa, maybe while people think about questions, can I ask a question? Do you think your book is well suited for people to learn about Python and quantum computing on their own? Or is it more intended as a book to use as a kind of material for a lecture? What was your thinking when you wrote the book?
Well, I think it's possible for them to learn on their own. It's a standalone book because we try to provide as much information as possible. So I think it's possible with examples. I think we have more examples. It's loaded with many examples. So it should be possible for people to learn on their own.
Okay. And you said all the example codes are also available online for people to start playing with it. Yes,
Prof. I prepared this notebook now, but there's also a GitHub repository for the book. So
okay, fantastic.
I just provided a few examples, but if they want more details, they can use the GitHub repository, yes.
And Makhamisa, do you want maybe to share in the chat the link to your GitHub or to where people can buy the book? I'm trying to be your marketing agent.
Yes, Prof. I will share maybe the link.
And do you know if we can buy it already in our local bookshops, or do we have to order it?
I haven't seen it in local bookshops, but I know it's on Amazon, so I'm not sure about.
Okay. Okay. If it is on Amazon, then we are fine. Yeah, perfect.
And the target audience for the book, I know it's an introduction to quantum information processing. In terms of target audience for students, would undergraduate students be able to pick up this book and still filter through the book easily, or it's more advisable for postgraduate students? So what is the target audience of the book?
I think it's more appropriate for the undergraduate students than the postgraduate students, because most of the stuff that is being covered is mainly the basic stuff, the introductory part.
Okay, very good. Then, yeah, maybe we will invite you, Makhamisa, to give a kind of a course for students online on how to use your book as a tool. Yeah, that would be very nice.
I hope so.
Yeah. Okay, it doesn't. Yazira, do you think there are other questions? I don't see raised hands.
None I see in the Q&A features yet. So.
Okay.
I think we just wait for Makhamisa to provide us the book, and I think you want to share some code with us, if I'm not mistaken.
Do this, yes. I think I've shared the screen. Can you see my screen now?
Not yet, Makhamisa. But if it is challenging, Makhamisa, at the moment, you can share the link with me, and we can share it with the participants and advertise your book. Yeah.
Okay, thanks, Prof. I think I'll just. It's like on dates, but the internet is also very slow this side.
Okay. No problem. Those things happen. We've been living for a year in Rome. We know how these things work. Yeah. Okay. Then, if there are no more urgent questions, Makhamisa, thank you very much for your time this morning. Congratulations to the nice book. And I wish you and the book all the best and a wide audience. Yeah, and we will maybe we will integrate it in our teaching on quantum computing in the near future. Yeah, Yazira, thank you very much for moderating the question, and Ilya, thank you as usual for being the co-host of the event. So maybe just a little preview. Next week we will have a completely different topic, which might be very controversial, but it's always good to listen to many different opinions. And the topic will be about energy solutions for South Africa. Yeah. And we have invited a prominent speaker, but we will share the announcement later today. So looking forward to next week again. Makhamisa, thank you very much, and all of you have a good day. Thank you. And
thank you. Bye bye.
Thank you. Bye.
Bye.